All right, second slideshow. This will go a little quicker. Talking about Portland cement, some Portland cement concrete, and asphalt concrete. Asphalt concrete is in the review or in the supplied reference. I have yet to be able to find an example, every review problem that deals with asphalt. But it's in the book. So if it's in the book, we need to make sure we know how to deal with it. Remember the different components for dealing with cement. If we got cement and water, it's cement paste. We got cement paste and sand, it's mortar. Add some aggregate in there, we call it concrete. We've got some different volumes, ratios there. Portland cement, 7.5 to 15%, 60 to 70% aggregate, 1 to 15%, although it's really probably more like 1 to 7 or 8% air. Water's going to vary, and of course the admixtures are very, very negligible in their volumes. That's what it takes to put together a decent concrete. Specific gravity of all cements are 3.15. We do everything in weights because it bulks so badly because of air content. When we look at hydration, that's the chemical reaction between the cement itself and the water, and that's going to produce all different chemicals, different reactions, and get the bonding or the glue, if you will, to turn concrete into concrete. When we look at the voids that are in our concrete, we've got entrapped air and entrained air. We like the entrapped air, or we like the entrained air. We don't like the entrapped air. The entrapped air is usually bigger in size, and it's gotten into the concrete by the handling and placement process. Entrained air is very, very small microbubbles that we like. Like those sizes, they help us with our durability and long-term conditions of our concrete. We do the Vicat needle test to help us determine the hardening or the setting process of our concrete. We've got an initial contact of the cement and the water. We start our clock. We can place the material, handle the material, do our fresh mix property tests with it. And then when we get a Vicat needle penetration of 25%, it tells us we've got an initial set for the material. At that time, things are starting to get into a plastic state. We can't move it around and manipulate it. If we do, it's going to be very blocky. Won't go back together, if you will. And then we eventually get to our final set with the Vicat needles, a 0 penetration. But that's the point where you can actually walk on it at that point if you wanted to. And that's the point that hardening begins. We have setting up till this point. Now we're getting hardening. And that's where we'll get our curve from our compression test. Water-cement ratio is a very, very, very important aspect for our Portland cement concrete, Abrams' law. And he realized that the ratio of water and cement were the key element in designing a concrete mix. For hydration to occur, you need between 0.22 and 0.25% water with respect to the cement content. Typically, though, in real concrete, we've got water-cement ratio is somewhere, ratio is between 0.4 and 0.7%. And we've got that so that we have workability. The 0.22 to 0.25 gets us the hydration to occur so we get our strength. The excess beyond that is so we can work it and manipulate it and move it. Yes, sir. Oh, really?
We don't have 3 or 4 or 7 and 8.
Well, you guys should have done a better job of copying.
Or 15 or 16. 11 and 12. We shouldn't keep going.
And it looks like every other
one is needs.
Holy cow. Let's hang on here now.
That's okay though, and I think we should just proceed and then get the handout.
So you gotta keep those two sets of numbers separate in your mind. One's for hydration and one's for typical concrete, so we have workability, extra water for workability. Water-cement ratio, like I say, is very critical for us. As the water-cement ratio gets higher, i.e. we get more water in there than we should have, decreases strength, decreases durability, decreases bond between layers, decreases bond between the concrete and the rebar. It increases the permeability, and it increases the chance for volume change. It does absolutely everything wrong we don't want to happen to our concrete. So we really got to keep track of our water cement ratio. Diagrams, and these are diagrams that are in the book. They could ask questions about this. As water cement ratio decreases, our compressive strengths increase. And we can see on here, if we look at the chart on the right, we can see how our compressive strength increases. If we had a 0.45, if we had a 0.45, okay. See what we can get going here. See if we can now make it work. You're seeing that too, right? That's frustrating. All right. If we had a 0.45 water cement ratio and we drew a vertical line up from that point, we could see what our compressive strengths would be for day 1, day 3, day 7, and day 28. In the real world, we typically think about our strengths and talk about our strengths in terms of 28-day strengths. But we could, with this chart, after 3 or 7 days, plot it and say, if we're getting the strengths we ought to be getting, because it ought to plot right. It ought to plot right on here. Got different types of cement, and I have seen questions like this. They'll give you the different types of cements, and they'll say, which one should you use for this application? You got type 1, type 2, type 1, 2, which is a combination you see more and more these days. Type 2 is for moderate sulfate issues. We got a high early strength, so we get our compressive strength quicker, so we can maybe take forms off earlier, speed up production if we're doing slip form operations. We have low heat of hydration kind of cement, so that if we're casting something big, this helps keep the heat down, because heat's our enemy during the curing process, the heating, the hardening process. And we got high sulfate resistance, so if you have high sulfate issues, and you put those in there for the different application that you're looking at for your particular design. We don't like entrapped air. It has all the bad effects. We don't want decreases strength, increases permeability, because the bubbles are connected. We do like entrained air. We'll talk about that in a little bit more. We have to put water in our Portland cement concrete for hydration. We like to keep that water cement ratio as low as we can, because it gives us the highest compressive strength we can get. But we also realize we've got to put some extra water in there for workability. If you can't move and handle the material and get it to consolidate where you want it to be, then there's no benefit to it. You'll frustrate people. So we've got to add enough extra water in there to make things work. So that's how we get that 0.4, 0.7 water cement ratios, because we have that extra water in there. We got water reducers that help us get material that can flow well. We can reduce the water cement ratio down where we like to get a high compressive strength, and then we can add some water reducers in there. Little misnomer in the term, the way it sounds. We're not really reducing the water by putting that in there. It's not reacting with the water, doing anything with the water. What it does is it allows us to reduce the water we put in the mix. We put some of this in there, a lot of times referred to as super P, super plasticizer, and depending on how much you put in there, I wish our pen worked. Yeah, all it's going to do is advance slides. You can see we have no water reducers on the far left there. Coming out of the slump cone, it stays in the exact same shape we put it in there when we formed it. We put conventional reducers, mid-range reducers, and of course we put the super P in there. It's a self-leveling concrete. It flattens out and will travel large distances and will flow around rebar easier and things of that nature. Got to be careful with the super P, though, that if you get too much in it, then it can cause aggregate segregation, because there's not enough solids. It's too fluid, and all the rock just drops to the bottom. And then you don't get good uniform concrete like we like to have. Got a retarder. That deals with our set time. That deals with our set time. It can delay or retard the set so we can work with it longer. haul it farther distances, move it farther on the job site, things of that nature. We've got things to help control the hydration. We can actually stop it, restart it if we'd like to. Here again, if you're on a job site, something goes wrong, you got long travel times, you want to do that so the material doesn't go into that into the setting process too quickly. We can put accelerators in there to speed up the initial and final set time. If you want to make things go faster, you can put those in there and get to that rigid state quicker. Doesn't affect your compressive strength at all. That doesn't change at all. It's just how fast you get to the hardening process beginning. And calcium chloride's the most common additive to cause that to occur. There's admixture for everything you can think of. These are a very, very short list, but you can add stuff in there for workability, for reducing permeability, for color, for reinforcement, to help it pump through a pump truck. You name it, there's an additive that you can put in there if you want to pay for it to be able to handle the concrete in its different methods or forms. We can add fly ash or slag to the concrete to replace cement because it's cheaper. Because it's cheaper, these actually become and replace the cement. So these are actually included in the weight of your cement for your water-cement ratio. So these are actually included in that. Fly ash has advantages. It doesn't get real hot. Slag has its advantages. They're trying to give it away like candy. So both of these and a lot of concretes will have these in there to help make the concrete more economical, keep it a little cooler, and have the same result, have the same compressive strength when you're done. Silica fume coming off the coal production process. There's other natural materials out there that you can put in there as well. They all can replace the cement, which is your most expensive component. Anytime you can replace that and still have the same product at the end, you want to do it. We got our different mix designs. The 1, 2, 3. You got a small or non-critical job scenario. You got by weight method, and you got by absolute volume method. Absolute volume method is a little more difficult, but that's exactly what we want to do. It's exactly what we want to do in our true mix designs. Weight method is pretty good, but it's not as accurate, but it's very easy. Arbitrary method 1, 2, 3. Can't get any simpler than that. 1 volume sand. 1 volume cement, 2 volume sand, 3 volumes coarse aggregate, mix that together, put some water with it, and you got concrete, and that'll give you decent concrete. So depending on what you're building, if you're out at the farm, 1, 2, 3 method works great. If you're running a ready-mix concrete plant here in Huntington, you better be doing absolute volume, because when somebody buys a yard of concrete, they want to be buying a yard of concrete. And any other methodology could be off just a little bit from that volume standpoint. Examples of the arbitrary method: you can use buckets, shovels, whatever you want to use to make that work. When we're designing our concrete, we're given a design strength we want to target, F prime sub C. We know that concrete's got a variability in its strength, and we don't want to design our mix to be F prime sub C, because then half the time it'll be acceptable, half the time it won't. So we're going to go back in and define that we want at least 90% of our samples to be good, with only 10% being bad. And if we go through this nice little slideshow here, we'll see that if I design to 1.34 times the standard deviation added to the compressive strength I want, that's F prime sub CR, which is the center of this bell curve, and that's where I want to design to. And that guarantees I'm going to have 90% of my mix will come out and test properly. So I'm going to accept 10% being off by going through this process. Depending on what your standard deviation is, what equations we're going to use, you want to find your weight, your water cement ratio. Somebody says I want F prime sub C to be a certain value, or F prime sub CR to be a certain value. Go into the simple chart, come over, come down, and that'll tell you what your water cement ratio is. This is a graph that's developed over time in your particular facility. It's from your historical records, what you produce historically. So when somebody else later on says I want 5,000 KSI or PSI strength, 5 KSI strength. You can come in with a 5, go across, come down. That tells you what water cement ratio you need to be using in your mix to get the proper compressive strength long term. We correct for our moisture. It's one of the biggest and most important things we can do. If we don't correct for moisture and we have free moisture in our aggregates, extra moisture in our aggregates, then we have to add that water by accident to our water cement ratio. So therefore, we're increasing our water cement ratio, means we're decreasing our compressive strength. So you got to watch. When you're doing that to make sure that you don't add extra water. If you had something that was drier than it's supposed to be, then it's going to make your workability rough. It's going to make your workability rough. So in this particular scenario here, when we did the design for this slide, we had 305 pounds of required water based on the water cement ratio, and based on this chart and looking at the absorption levels for the aggregates, the actual moisture contents today, we end up with almost 56 pounds of extra water in the aggregate because it was wetter than saturated surface dry. Therefore, we have to take the 56 pounds off of the 305 pounds and only put in 249 pounds. If we put the 305 in, we would have got the 56 by accident. Our water cement ratio would have tanked on us. It would have tanked on us. The importance of proper curing your concrete. Do all the mixed design in the world and get it perfect. But if we don't cure the concrete correctly, this is an indication of what kind of compressive strength you're going to get. Cast the concrete and don't do anything for it. Dry it in the air the entire time. When you thought you were going to maybe get 3,000 PSI concrete, you're going to get 50% of that. Your y-axis here is 50% of the compressive strength at 28 days. So if you wanted to get the maximum value out of your concrete, you moist cure it, keep it cured when it's going through its hardening process, and you will get more than 100% of your design strength. So the longer you leave it out, the lower your compressive strengths are going to be. Diagram of compressive strength versus strain. And as you see, we get our water cement ratio 0.33. It's down in that area we like to be at, 0.4, 0.5. We see nice stress strain curves. We don't get a lot of strain before we get our compressive strength. As we get higher and higher water cement ratios, not only do we get lower and lower compressive strengths, it takes longer to get to those compressive strengths. And we don't like that. We don't like that. So rule of thumb, make sure you're keeping your water cement ratio where you want to be. Estimation of modulus of elasticity. Here again, that's just in the book. If they give you that prompted C, find the equation and get your modulus of elasticity. Different tests for testing concrete, hardened concrete. We've got destructive and non-destructive. Compressive strength, splitting tensile, flexural strength. We did compressive strength testing in the lab. We did flexural testing with the beam. We did not do splitting tensile, where we set the cylinder on its side and do it in tension. Non-destructive testing, there's rebound hammers, penetration resistance. Both of those are more of a surface texture, surface hardness, trying to correlate that to the compressive strength of the entire mass, but you're only testing the surface. Ultrasonic, maturity testing, those are two different forms to try to keep track of what your compressive strength is. Maturity testing is really a long process you have to do up front. You can't do that post-construction. You have to have done that in the lab prior to going out there. I don't think you're going to see anything on maturity testing on the lab. Compressive strength, putting load on the sample, busting the sample. Splitting tensile, put it on its side, measure that load, and we're measuring the tensile capacity. We always talk about concrete not having tensile capacity. It has a very small amount, about 10% usually of the compressive strength. I've seen questions like that. What would be the most likely value of the tensile strength for this concrete? And they give you the strength of the concrete, and you have to do the quick math, come up with about 10%, and that tells you what the tensile capacity could be. Flexural beam, you've done this in class, 3-point loading. Asphalt. Like I said, I haven't seen a lot on asphalt, so we'll click through this even faster. You got bituminous materials, asphalt tars. We get most of all our products this day out of asphalt because it's easier to control. We've got cements, cutbacks, and emulsions. Make sure you have a good feel for the difference between those and how they're placed. Very temperature susceptible, as we all realize. Summertime, you can feel asphalt getting soft under your feet, right? So it's very temperature susceptible. Therefore, it's very difficult to design with from the standpoint you got to make sure that it can handle both the cold temperature and the hot temperature in the region you're in. The kind of asphalt concrete you use in Florida is not the same one you're going to use in Minneapolis, Minnesota. If you take the asphalt concrete from either one of those, take them to other places, it will fail miserably very, very quick. So you got to make sure you got your temperature ranges properly set for this material to work good. Too brittle, you're going to have problems. If it's too soft, you're going to have rutting. So you got to make sure you're in that sweet spot in the middle there. Make sure your grades are set properly. Thermal cracking, that's what you see right there in that one photograph on the left. On the right, you're seeing rutting, and those shadows you see there, that's actually tractor trailer truck tires that have rutted that as it rode down the road there. Grading systems, I haven't seen anything on any of the exams I've ever seen, example exams I've seen on grading, but it's in here because I had it in the class. When we look at how we rate materials nowadays in the asphalt world, it's on performance. Used to be we just had a set of properties and we tried to emulate those, and we felt that those gave us good results in the field. Nowadays we're going back and looking at the specific behaviors we want to see and rating the asphalts based on that and designing based on that. So it's about performance these days, not about the design properties we thought were the right properties. Looking at the grades of asphalt, what temperature zones you need to be in, different type of asphalt. Super pave is the new design methodology you've got out there everybody's using, and it's based on performance, based on getting the performance out of the material so it'll last like we'd like to see it when it's placed. I'm going to jump through this super pave stuff. Like I said, I haven't seen a problem like this on the exam, so we'll try to move through here a little quicker. Super pave. So that's everything on that particular slideshow. Now the challenge is going to be to see if I can get the screen to work here. So we can record what we're doing. Oh, wait a minute, let's try this. Maybe they've actually got it installed. That doesn't look like what we're after here. There's what we're after right there, maybe. These are all websites. And now it won't let me out. All right, so now we're going to look at a bunch of problems. A lot of this is going to be reading problems and writing them up here on the screen for you. I do have all of these. You're more welcome to copy any of these you want to. If you want to work on them on your own later on. Let's see. A ready-mix concrete being delivered to the job site is found to have a slump less than specified. Which of the following is the most appropriate corrective action? Decrease the amount of water in the mix before the truck leaves the ready-mix plant. Increase the water in the mix in the truck at the job site before the concrete is poured. We don't use the word poured, right? It's placed. Add an admixture to the truck at the job site before the concrete is poured. Increase the rotation speed of the mixing drum while the truck is in transit to the job site.
What was that question again?
Ready-mix concrete is delivered to the job site and is found to have a slump less than specified. So it's too stiff. Too stiff. Which of the following is the most appropriate corrective action? Decrease the amount of water before it left the plant. Increase the water at the job site. Add an admixture to the truck at the job site. Or increase the rotation speed while it was coming down the street.
I would say C.
B, throw some water in the truck at the job.
B is throw the water in the truck at the job site. What has Professor Huffman said 8,000 times?
They do it all the time.
You can if on the ticket it says you're allowed to. And on the ticket sometimes it'll say you can add up to a gallon or 2 gallons a yard, whatever it might be. Typically it's highly frowned upon to add any water to the job site. Because what are you doing? You're lowering your compressive strength. So the proper answer is you need to add an admixture. Maybe you could add in a little bit of air training agent, make it work a little better. You can add a super P agent, a water reducing agent in there, and that will help increase the fluidity of it so you can actually move it and place it. Oh, that when you start looking at adding in some kind of water reducer, you can make some thin concrete real quick, real quick.
We switched Super P types.
We switched, yeah. That your guys' year we switched types and it was real. It was off the chart. It was off the chart.
Yeah, ours went off the board and everything.
In general, and that's the way a lot of these materials type questions are going to be, unfortunately. It's just a quick answer. In general, a metal with a high hardness will also have good formability, high impact strength, high electrical conductivity, high yield strength. High yield strength. Correct. Glass is said to be an amorphous material. This means that has a high melting point, has a supercooled vapor, has a large cubic crystals, and has no apparent crystal structure. Has no apparent crystal structure. You can see through glass, right? You can see through glass. Has no apparent crystal structure. An aluminum crimped connector used to connect copper wire to a battery. What would you expect to happen? The copper wire only will corrode. The aluminum connector only will corrode. Both will corrode, or nothing. You've got an aluminum crimped connector connecting a copper wire to a battery. The aluminum will corrode. The aluminum will corrode. A steel bar is tested in tension at a stress less than the yield strength. At less than the yield strength. The module of elasticity is most nearly axial stress divided by change in length, axial load divided by change in length, axial stress divided by axial strain, axial load divided by axial deformation. Stress over strain, right? C. Axial stress divided by axial strain. All this junk up front about the steel bar was tested in tension to its yield strength has nothing to do with the question. Make sure you read the question. All you need to know, all this question needs to say, the modulus elasticity is most nearly. All the rest of that stuff was fluff to try to confuse you, to try to figure out, so maybe you're trying to use yield strength and you calculate your answer somehow. Plausible distractors. Plausible distractors. You got to be careful with those. Yeah, we're probably going to skip that one. Let's skip that one. Don't want to be here all night, do we? Flipping through these. Which of the following properties cannot be determined from a tensile test? So that's tennis ulcer. We're grabbing hold of the two ends of it and we're pulling it. What cannot be determined? The modulus of elasticity, modulus of resilience, endurance limit, ultimate tensile strength. Endurance limit. Because endurance is going to be some kind of taking the paper clip and bending it till it breaks type thing, right? Mechanics of materials, mechanics of materials. What do impact tests determine? Hardness, yield strength, toughness, creep strength. What do impact tests hardness? What is the main difference between cast iron and steel? I won't even read the answers. Surely I knew you'd know that one. Surely I would know you'd know that one. Here's a good one. For a fixed curing time, the ultimate strength of the concrete increases with decreasing moisture content, decreases with decreasing moisture content, is independent of the moisture content if cured for a significantly long time, is independent of curing pressure. For a fixed curing time, the ultimate strength of the concrete increases with decreasing water content, decreases with decreasing water content, is independent of the water content if cured long enough, and is independent of curing pressure. Have you ever heard of curing pressure? I never heard of curing pressure either, so we cross that off. First option A. As water content goes down, water cement ratio goes down, compressive strength goes up.
Yeah, the curing pressure.
The curing pressure, whatever the heck the curing pressure is. It's got curing on the brain. Curing on the brain. See what else we have here. Just think if you could take this test as a group. Couldn't you just crush it? You could just crush it if you could take it as a group.
Way too much time in discussion, though.
You might. Continuous yielding of a material under constant stress is known as failure, strain, creep, or ductility. Continuous yielding of a metal under constant stress is known as, the answers are failure, strain, creep, or ductility. So we got continuous yielding under constant strain. So I got increase in strain, I've gone up, and then I've got to one stress level, and I've got constant strain moving to the right. So it is a form of yielding, without a doubt. It's creep. That's what the definition of creep is. A constant load, and you keep getting that strain over time. See, the mass of an atom of nickel is most nearly. Look at all the faces. Sorry. I had to do it. I had to do that one. Somebody knows that off the top of their head. Not the civils, right? Do what now? Oh, now you make me have to go back and find it. 2.1 times 10 to the negative 23 grams per atom is one of the answers. I don't know which answer is the correct answer. We're civils. That's close enough for us, right? Let's see here.
When you round it, it's 0.
In the civil world, it is. It's not. Oh, more the same thing. More the same thing. More the same thing. Like I said, there's just not that many. All of the metals, all of the following metals will corrode if immersed in fresh water, except copper, nickel, chromium, aluminum. All of the following materials will corrode if immersed in fresh water, except copper, nickel, chromium, aluminum.
I'm going to say chromium.
You're all wrong. It's copper. Copper. The process of annealing can be used to achieve all of the following, except annealing can be used to achieve all the following except relief stresses, recrystallization, grain growth, or toughness. Well, I was looking at it, and it's like it's kind of odd wordage, I think. It's actually toughness. It's actually toughness. When you anneal something, it doesn't really change the toughness. It does deal with stress relief. It does deal with recrystallization. It does deal with grain growth. Here again, you're starting to get into metallurgy when you start talking about things like that, and we don't talk about that in our materials course. We don't get into it that deep. That's a material science type question. This is a free one here if you got it on the test. The elastic modulus, yield strength, ultimate tensile strength, and ductility of a metal can all be determined from the elastic modulus, yield strength, ultimate tensile strength, and ductility of a metal can be determined from an endurance test, an impact test, a quenching test, a standard tensile test. Standard tensile test. That's a free one if you get that one, right? Which of the following may be a Poisson's ratio for a material? Negative 0.37, 0.25, 0.55, 1.5. And that's the question. They could throw that one at you in 2 seconds. Tells you if they know anything about Poisson's ratio, right? Negative 0.37, 0.25, 0.55, 1.5. 0.25. Because it's between it's between 0 and 1. It's 0 and a half. Typically more between 0.1 and 0.4. In the soils world, we're always about that 0.3, 0.35 range. So you'd love to see one like that. It's easy, quick. Easy, quick. And that's the way a lot of these end up being. What does the Sharpie test determine? Endurance, yield strength, ductility, toughness. Toughness. Here's a unique way of phrasing it. What is the ratio of stress to strain below the proportional limit called? The modulus of rigidity, Hooke's constant, Poisson's ratio, Young's modulus. Let's see what else we got here. We're getting close to the end of the stack here, guys. And a lot of these are going to be embedded in other problems these days. Let me see if I can actually draw this. Ooh, here's where we're supposed to be able to do this kind of thing. Are we all impressed or what? I impressed myself with that. Wasn't done. Wasn't done. This is point O. O prime. This is 2, this is curve 1. D, C, E, F, G, and H. I believe I have it all. For the stress strain curve of carbon steel shown, curve 1 is a plot of the true stress strain, the engineering stress strain, the tensile force versus elongation, modulus elasticity. It's the true stress strain. The slope of the line OH is the true stress strain curve, an engineering stress strain curve, tensile force versus elongation, the modulus of elasticity. Modulus of elasticity. Curve 2 is the engineering stress strain curve, correct? The slope of the line OE is the secant modulus, proportional limit, yield point, or ultimate strength. It's a secant modulus. Random point on the curve back to the origin. Point H indicates secant modulus, proportional limit, yield point, ultimate strength. Proportional limit into the linear portion there, right? Point F indicates proportional limit, yield point, ultimate strength, the permanent set. Proportional limit, yield point, ultimate strength, the permanent set. Have you ever even heard that last one before? Cross it off. It's not D. Proportional limit, yield point, ultimate strength. Well, what's the ultimate strength? F. Where's the ultimate strength at? D. We know that's not it. We're down to 2. What did we just say the proportional limit was? Solved it and didn't even know what the answer was, right? It's actually the yield point. Actually the yield point. Well, that is, the G on that is going to be your point of elastic limit. You can go to G and then come back. You can go to G and come back. And my diagram is maybe not the greatest diagram in the world, but when you get up in that point and you're getting stresses, you're getting strains without increasing stresses or decreasing stresses, that's yielding. So that's that yield point. If you had the diagram, you might be a little more clear. So a little hard to draw that on the screen. No, I think once you answer it, I think you're done. Now you can answer. I think you can mark an answer, but not like submit it. I think or something like that. Unfortunately, you're asking the wrong guy. I can ask one of the students have already taken the exam about clarification on that. And you might be able to find that on their website and explain how to take the test. Point D indicates the ultimate strength. Point C, fracture point, elastic limit, point, or ultimate strength. So it's going to be the fracture point.
Fracture. What's the ultimate?
Ultimate's going to be D. Ultimate strength, right? Right, ultimate strength. I didn't even put an X on there. Where's the X at? I don't see X on there. Oh, different diagram. Different diagram. Anyway, going to the next page here. What are you talking about? I can draw it all day long. I thought when I did this, it would give me new. Oh, there we go.
You're on new 2. That's what you're all on. They're all the same thing.
I know one way of getting there. To zap it. All right. When in doubt, hit the power button, right? This is one colored area in here. This is another one underneath here. I know. We don't have that kind of time. We all want to get home, right? Oh, mercy, 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 mercy. We got an X, and we got a Y. Area X represents the modulus of elasticity, the modulus of resilience, the modulus of toughness, Young's modulus. Modulus of resiliency, B. Y is the modulus of toughness. Modulus of toughness. And actually, I'm misrepresenting that. Y actually comes all the way down to here. Poisson's ratio is the ratio of the true stress to true strain, the lateral strain to axial strain, shear stress to shear strain. Actually, it is lateral strain to the axial strain. Most engineering work is based on engineering stress and strain rather than true stress and strain because engineering stress and strain is more accurate. Engineering stress and strain is easier to use. Design using ductile materials is limited to the elastic region where there is little difference. Reduction of cross-sectional area of parts at their service stress is well known due to Poisson's ratio, but it is needlessly complicated. Engineering stress, engineering strain is more accurate. Engineering stress and strain is easier to use. Design under ductile materials is limited to the elastic region where there is little stress difference or little difference. Reduction in cross-section area of part at their service stress is well known due to Poisson's ratio, but is needlessly complicated. C. Because C is design using ductile materials is limited to the elastic region where there's little difference. We don't want to take something out and get it beyond that plastic, in that plastic region, right? Because then we're getting crazy deformations. We don't like big deformations. We want to stay in that elastic region in there. And in that region, they're both the same exact curve. So it doesn't matter which one you want to say you're using. They're going to give you the same result. copy this all the same questions again. Um, Zero. Absolutely zero. Each of these questions got to be 2-3 minutes in length. I doubt it. I doubt you. Well, you might see the mixed water portion. You might see that little piece of it, but these are quick. These are boom, 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 boom. You just don't have time. These are all the same questions over and over and over. A soft material. A soft material shows low ultimate strength, shows high ultimate strength, exhibits a low modulus of elasticity, yields little before breaking. A soft material shows low ultimate strength, shows high ultimate strength, exhibits a low modulus of elasticity, yields little before breaking. So if something yields little before breaking, what do we typically think that's going to be? It's going to be brittle. It's not soft. C. Exhibits low modulus of elasticity. A weak material shows a low ultimate strength, a high ultimate strength, exhibits a low modulus of elasticity, and yields little before breaking. A, low ultimate. A hard material shows the same exact answers. Shows low ultimate strength, shows high ultimate strength, yields little before breaking, exhibits a high modulus of elasticity. Hard. A hard material. Low ultimate, high ultimate, yields little before breaking, or has a high modulus of elasticity. What did we just say for the low one? It's going to have high modulus of elasticity. The other one was low, right? Weak. Weak was low ultimate strength. We're talking about hardness here. Not talking about the brittle material. Shows low ultimate strength. Yields, and these are tricky. These really determine whether you know what you're doing. A brittle material shows low ultimate strength, yields greatly before breaking, yields little before breaking, exhibits a high modulus of elasticity. Yields little before breaking. The division between cast iron and steel for carbon content is 0.1, 0.72, or 4.4. 2%. 2%. The division between cast iron and steel, structural steel, the dividing line is 0.2. Or I'm sorry, 2%. 2%. Seeing the same thing over and over and over here again. Steel is the most prevalent engineering material for all the following reasons except. So which one's not true? The abundance of iron ore, its low density, simplicity of production, predictability of performance. Low density, right? Low density. Steel is the most prevalent engineering metal because it's in abundance. It's simple to produce. Well, it's compared to a lot of things. Predictability of its performance is known, but it does not have a low density. Unit weight of steel, 500 pounds per cubic foot. Massive density. All the following are common constituents of concrete except Portland cement, sand, aggregate, calcium chloride. Key there's common. Do you put calcium chloride in concrete? You do. Accelerates it if you do, but it's not the common material. The ratio of 1:3 for a concrete mixture gives the relative weights of which of the following constituents. So it's 1:3. Cement, coarse aggregate, water. Cement, sand, and water. Cement, fine aggregate, coarse aggregate. Water, fine aggregate, coarse aggregate. Cement, fine, coarse. The addition of steel to concrete is primarily to increase material density, increase torsional strength, increase tensile strength, increase abrasion resistance. Increase the tensile strength. We're getting there. The use of admixtures, hydrated lime, fly ash, etc., with concrete is to reduce weight, increase durability, improve workability, hardness, strength characteristics, accelerate curing. C, workability, dealing with hardness. Well, here about steel and recrystallization of steel, which doesn't do us any good. And a lot of the same questions over and over here. That's it. Got to the end of the book. Any questions in particular, anything we can clear up before we get out of here? Glad you guys could show up. Good luck on the exam. I know you all will do just fine.
So will I be able to bring my films?
No, you won't be able to bring anything in there.
Do they have a competition?
Yeah,